Hello everyone, I'm Norman Wahlberger. In this famous math problem, we're going to look at how to set up the theory of fractions. Of course, very important topic, primary school education, foundation for algebra. But actually the theoretical setup of fractions is quite subtle, as we'll see. Now, we are not actually looking towards trying to figure out how to educate primary school students in the optimal way in this direction. Rather, we're just here interested in this theoretical, pure math question of how do we actually efficiently set up the theory of fractions so that it's actually logically correct. Okay, so this is the usual way we think about fractions with addition, multiplication, division operations as being quite important. We're interested in setting this up correctly, and I think it's a relatively difficult to solve problem, of course. And our approach is going to be to start with the natural numbers and then to build up a theory of fractions based on that. And we're going to avoid subtraction by just concentrating on the positive side of things. So we're not talking about rational numbers, we're talking about fractions. And there will be a little bit of new notation. We'll actually not represent fractions this way, but rather in a slightly different way. Okay, so our starting point is the theory of natural numbers, just the ordinary counting numbers, starting 1, 2, 3, and so on. Notably, we're not going to include 0 in this discussion. Let's make that very clear. So usually 0, maybe we denote that with a nat plus when we want to include 0. We are not including 0 here, all right? So we're starting 1, 2, 3, and so on. And the primary operations are addition and multiplication, for example, these familiar examples. And the laws of arithmetic for natural numbers, well, there's the commutative law that apply to both operations. There's the associative laws, which apply to both operations. And then there's the distributive laws that connect the addition and the multiplication. So this is our starting point. So now what we want to do is we want to first define exactly what a fraction is. We want to define the operations on fractions. And then we want to prove the laws of arithmetic for them, which are more or less just these laws, but extended to fractions. Okay, so the main definition of what is a fraction. And I want to emphasize that we're talking about fractions here and not rational numbers. Rational numbers are close to fractions, but they're a little bit more general. So from our point of view, rational numbers are analogous to fractions, but built up from integers rather than from natural numbers. Okay. So what is a fraction? A fraction is an expression of the form a over b. So there's a number here, there's this forward slash, and then there's a b, where a and b are natural numbers. So that's what a fraction is. It's an expression of this form involving three things. Okay? A natural number, a forward slash, and another natural number. But importantly, with the following convention for equality, we'll say that a over b equals a prime over b prime, precisely when a times b prime equals a prime times b. So it's a little bit more subtle than just defining an expression. We're defining an expression with an attendant definition of equality. So we're allowing the possibility that two expressions that look different actually represent the same fraction. And there's our name for the type of object that we're introducing. Okay, so for example, 3 over 4. Okay, and I'll say over to represent this forward slash. 3 over 4 is obviously a fraction because it's in the right form. And 3 over 4 is equal to the fraction 6 over 8 because 3 times 8, which is 24, equals 6 times 4. How about 5? Is that a fraction? Important question. Is 5 a fraction? You just look at this. Does this fulfill the requirement of the definition? Obviously, the answer is no, it's not. Okay? This is just a single natural number. To get a fraction, we need two natural numbers separated by a forward slash. How about 0 over 1? Is that a fraction? No, it's not, because 0 is not in our natural number system that we're starting with. Okay? That's also important to observe. Now we do not have a 0, so we do not actually have to make the extra requirement that the denominator, b, is not 0. That's automatically true because of the restriction that all of the numbers we're talking about are natural numbers starting with 1, 2, 3, etc. And minus 8 over 3, that's also not a fraction because we're not including negative numbers. All right, now let's introduce the primary operations on fractions, which are addition and multiplication. Okay, so here's the definition of addition. If you have a over b and c over d, here's the sum, a over b plus c over d. It's by definition AD plus BC over BD. And the product of those two numbers, a over b times c over d, is, by definition, the fraction a times c over b times d. So this is how we're going to define addition and multiplication for fractions. But, and it's a very important but, there is a crucial proviso that we have to check first. As it stands, these are not entirely proper definitions because they are not necessarily well defined. What do we mean here? Well, we've agreed that a fraction can have different representations. There's a notion of equality for fractions. That means that there is the potential difficulty that if we multiply this fraction with that fraction, and then replace this one here with something that's equal to it but looks different, that the new product will be actually different from the first one. We have to make sure that things are well defined. Okay, so let me clarify that. We'll do the multiplication first, okay, which is a little bit easier. So I want to show you that multiplication is well defined. So how do we set that up? So suppose that a over b equals a prime over b prime. So these are two different representations of the same fraction. And over here we have another pair, c over d equals c prime over d prime. Now what does that actually mean? So the equality means that a times b prime equals a prime times b. And this equality means that c times d prime equals c prime times d. We're going to have use for these two things, so let's call them condition 1 and condition 2. So now what we want to do is we want to show that if we take the product of a over b and c over d, we get something. And we compare it to what we get when we take the product of a prime over b prime and c prime over d prime, that these two results are also equal. So this fraction is the same as that fraction, this fraction is the same as that fraction, so we want that the result of this product is the same as the result of this product. Now what does it mean for this fraction to be equal to this fraction? It means that AC times B prime D prime equals A prime C prime times BD. Okay, so this is the condition that we want to satisfy. But by associativity, we can rewrite this. Okay, here we have A times C times B prime times D prime. We can remove the brackets, and then by also commutativity, we can rearrange this to be A times B prime times C times D prime, this left-hand side. And then over here, we can do the same thing. We can rearrange it to get A prime B times C prime D. We want to prove this. Well, this is just the product of these two relations. This is relation 1, AB prime equals A prime B. This is relation 2, CD prime equals C prime D. If we take the product of these two things, we're going to get AB prime times CD prime, which is the left-hand side here, equals A prime B times C prime D, which is the right side of what's up here. So the equality between these two things is a consequence of the relations that we're assuming between A, B, and A prime, B prime, and these two here as well. All right, so that proves that multiplication is well defined. Okay, now let's correspondingly look at the other operation of addition and show that it's well defined also. So we want to show that here's A over B plus C over D, and that's the form of it, using the rule of addition. And here's a prime over b prime plus c prime over d prime, the form of it with respect to addition. And we want to show that these two things are equal, assuming as before that these two are equal and these two are equal. So equality between these two fractions amounts to this AD plus BC times B prime D prime should equal this A prime D prime plus B prime C prime times BD. Okay, so let's expand this out. We expand this out here. AD B prime D prime plus BC B prime D prime on the left-hand side. On the right-hand side, A prime D prime BD plus B prime C prime BD. We want to prove this. Okay, what do we know? We know that AB prime is equal to A prime B. That's our condition 1. And we know CD prime equals C prime D. That's condition 2. So the left-hand side of this equation, the left-hand side, we can write it like this. Over here, this term A, B prime, we can bring them together, and then there'll be a D, D prime. So we're just sort of rearranging the 4 terms here, grouping them a little bit differently. And this one here, also we bring the B and the B prime together, and then there's a C and D prime left over. And now we can replace this A, B prime with A prime B from 1. So we get A prime B times D, D prime. And we can replace the C D prime over here with C prime D using condition 2, which gives us B prime times C prime D. And now we look at this and we compare it to the right-hand side of this. The right-hand side is A prime D prime B D. So that first term is exactly the same as this one. And this one here, B prime B, there it is there, C prime D, there it is there. This is just a rearrangement of that. So yes, indeed, we do get the right-hand side. So this is a true equality, and this follows from our conditions 1 and 2. Now, this is not really hard, but it's not really easy either. And so you see that there's an interesting logical question. When you were learning fractions, did you ask yourself this question? We have these multiple ways of representing a fraction. We have these multiple ways of representing another fraction. How do we know that our procedure for adding or multiplying these two things is independent of which representative we choose? It's a subtle issue, and I think it's fair to say that most primary school students would be dismayed by this proof. This would be too abstract, too algebraic. This is something that you might learn in high school, okay? And probably you should learn it in high school when you're learning a little bit of algebra. But I think for most students, this probably slips through the cracks. I wouldn't be surprised if less than 5% of undergraduates actually have ever seen or gone through the proof that these two operations are well defined on fractions. So now that we have the numbers themselves and we have their operations defined, we want to establish the laws of arithmetic, like the commutative, associative, and distributive laws. So let's let P be A over B, Q be C over D, and R be E over F. So here are 3 fractions. And the laws are expressed in terms of P's, Q's, and R's. So there's the commutative law, that P plus Q equals Q plus P, the addition one, and the multiplicative one, P times Q equals Q times P. Okay, so what does this one amount to? Well, P plus Q, what is that? We have to add these 2 fractions. So we get AD plus BC over BD. And Q plus P in the other order, so you have to interchange the order, you get C times B plus D times A, all over the product DB. And a moment's thought shows that these are the same because the numerators, the things on the left, are the same, just a rearrangement, and the denominators are the same, just a rearrangement. And similarly with multiplication, the product P times Q is AC over BD, while the product of Q times P is CA over DB, and obviously these are the same because of the commutative property of multiplication of ordinary natural numbers. Okay, then we have the associative laws. P plus Q plus R equals P plus Q plus R. Okay, it's a little bit more involved. So P plus Q, there's that fraction. R is E over F. And then we want to prove that's the same as P, which is A over B, plus the sum of Q plus R is CF plus DE over DF. Okay, so what is this left-hand side here? Well, that's one fraction plus another fraction. So the sum is the numerator here, AD plus BC times F plus BD times E. That's the top. And the bottom is BD times F. And over here, similarly, we combine these two using addition. So we get A times DF plus B times CF plus DE as the numerator there. And the denominator is B times DF. Okay, so these two fractions are equal. How do we check that? Well, we know how to check equality for fractions. We have to take the numerator here, so the numerator is the thing on the left, the denominator is the thing on the right. We take the numerator here and multiply by the denominator here. Okay, so there it is there. We've expanded out a little bit. Multiplied by B, D, and F. We can dispense with the brackets because we know that the multiplication of natural numbers is associative. And that's supposed to equal the numerator here, which we've expanded out, times the denominator there. And then you just check term by term that, in fact, we get the same terms on both sides. The two products are the same. And for multiplication, it's the same kind of thing. P times Q is that thing there multiplied by R, while P times Q times R, there's P and there's Q times R. And when we multiply that again, we get AC times E over BD times F. And on the right-hand side, we get A times CE over B times DF. And again, by associativity of ordinary numbers, this thing's the same as that, and this thing's the same as that. So these expressions are indeed the same. Okay, and here's the distributive law. One of them, I'll leave the other one to you. Here's P times Q plus R equals P times Q plus P times R. Okay, so using the same notation for P, Q, and R as before. Here is P, it's A over B, times Q plus R. There is Q plus R. CF plus DE all over DF. And on the right-hand side, we get P times Q, the product of these two, so that's AC over BD. And P times R is the product of these two, so that's AE over BF. Okay, so let's have a look at the left-hand side. The left-hand side, it's a product of two fractions, so the numerator is A times CF plus DE, the denominator is B times DF. And by expanding this, we get ACF plus ADE over BDF. What about the right-hand side? Well, that's a sum of two fractions. Okay, so we have to take AC times BF plus BD times AE, that's the numerator, divided by the product of BD and BF. Now we expand this out and simplify it. There's a common factor of B in both terms, so we can pull that out. Then we get ACF plus ADE remaining in the numerator. And over here there's also two factors of B, so we can pull one of them out, and the remaining thing is BDF. And now I claim that this is actually the same as what you get when you lop off the B's. So this is the same as just ACF plus ADE over just BDF, which is what we got in the left-hand side. So what we've done here, okay, we've used the following important simplification. That if we have B times some number X over B times some number Y, that fraction is the same as just X over Y. And the reason, of course, is simple, because the equality property is just amounting to bx times y equals by times x. Those are obviously equal. But we have used this sort of cancellation. We've canceled a b from the numerator and the denominator here to get this right-hand side equaling to the left-hand side. So again, it's not really hard, but it's, it's a little bit subtle. Okay, and it's a nice kind of application of algebra because we're establishing these fundamental laws of arithmetic for the realm of fraction arithmetic. So why do we have an arithmetic with fractions anyway? That's an interesting question. So one obvious answer is because it's connected to the abstract theory of algebra. So it's just a useful tool to learn how to manipulate things in certain ways. But a more sensible answer is probably that it connects with the real world in that when you're dividing things up, okay, fractions naturally occur. So fractions are associated to wanting to do division. Division is always the bugbear of arithmetic. Okay, so if we have natural numbers, we can do addition and multiplication very well. We can do subtraction kind of half of the time. Subtraction is a little bit more problematic, but division is much more problematic. So 24 divided by 6, yes, we can do that. We can look up the multiplication table. Remember that 4 times 6 is 24, so 24 divided by 6 is 4, fine. But 24 divided by 5, or 24 divided by 7, that leads us outside our number system, and suddenly we are not in a good position to deal with that. And so one justification for fractions is it allows us to implement division more smoothly. Okay, so we definitely want to sort of include this now in our framework for fraction arithmetic. So let's introduce division. Okay, and a nice way of doing that is to start with inverses. The inverse of a fraction a over b can be defined to be just the fraction b over a. Then you have the nice property that when you multiply a fraction p by its inverse, you get the fraction 1 over 1. And at this stage here, we can say, look, this is a very nice special fraction. It deserves a special name. It acts like the number 1 in the natural numbers. In the fraction world, this fraction is playing the role of 1, so maybe we could even call it 1. But we'd have to make that agreement. We'll have to say, look, we're going to agree that this particular fraction is represented by 1. Okay, so then this allows us a consistent new operation of division. We can define division this way, that a over b divided by c over d is the same as a over b times the inverse of c over d. Okay, the inverse of c over d is d over c. So this product is just AD over BC. So you could also define it directly if you wanted to and avoid discussion of inverses. So great. So there's a few more laws of arithmetic that you could then write down that include division also, and you might have some fun doing that. And now it seems maybe that the circle is closed and we're kind of finished. So we've defined what our fractions are. We've introduced the operations quite concretely and carefully, and we've checked laws of arithmetic for this nice domain. But it turns out that we are not finished. And that's why this problem has a difficulty level of 4 and not 2 or 3. Because actually there's more to be done before we actually have a system which is actually practically of use. This is all theoretically very well. But if you actually start working with just this framework, you quickly run into some very obvious numerical problems. Okay? And I want you to think about what those are. So more work is needed, and I give you the challenge of trying to figure out what that is before I talk about that in my next video. Hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.